So again, welcome everyone to the second session of the second day of Limit Camp. Uh, Today we have Shubham Sharma. He did his BTech from BITS Pilani and Masters of Mathematics from ISI Bangalore. And he is a incoming graduate student at Michigan State University. Today he will be talking about an invitation to several complex variables. So over to you, Shubham.
Yeah, thank you. Uh, yeah, hi everyone. So I hope I'm audible, and if at any
Yeah,
point there is some doubt or there is some question, or you want me to repeat something, just let me know. So let's. So my aim here today is just to give a motivation to encourage people to look at several complex variables and maybe give an insight into why I have found it interesting, how much or little I have studied. So let's start by thinking about what we know in our undergraduate education and even in our master's education. We see real analysis and many other subjects related. We see multivariable real analysis, we see functional analysis, we see measure theory. But what about complex analysis? We never see several complex variables, or we never see how the relation between complex manifolds and holomorphic functions, things like that, right? So why is this not a part of our system? Is it because several complex variables are too similar to the one variable case, or is it because they're so advanced and so different that it's not approachable by undergraduate students? Well, actually, neither of those things is true, and hopefully, by the end of today's talk, uh, I would have convinced you to look in deeper into several complex variables. And the second reason why I personally find a several complex variable very interesting is that one finds that there are applications of many other fields in several complex variables. For example, one of the famous problems in several complex variable has solutions coming from algebraic topology, in particular sheaf cohomology, and various aspects of algebraic geometry and functional analysis and convex geometry also find applications in several complex. So, and by the end of today's talk, hopefully, I'll be able to convince or I'll be able to show you the deep connection between several complex variables and convex geometry in particular. So let's start with something that we all know, that is how do we define uh, for functions which are multivariable functions from Rn to Rm? How do we talk about differentiability of such functions? Recall that we say that such a function is differentiable if this limit, so that if there is a linear map written by dfa from R at the differentiable at the point A, which is a vector in Rn or a point in Rn, then this map is differentiable at the point A if there is a linear map dfa from Rn to Rm such that this limit f of a plus h minus f of a minus df a h upon norm h goes to 0. Right? And in particular, we find that this dfa ends up being the Jacobian. This DFA ends up being the Jacobian of the function f. And recall the Jacobian is just so since this is a function from Rn to Rm, f is actually made up of functions of the form f1 fm, where each fi is from Rn to R, and or each fj is from Rn to R, and the Jacobian is del f1 by del x1 and del f1 by del xn and so on. So now let's see how. So when we go to complex differentiability, the one way to think of we all know that C is topologically similar, topologically this homeomorphic to R2, or it's the same as R2, equivalent to R2 in some sense, at least topologically. So often we will treat functions from C to C as functions from R2 to R2, and we will consider the function x comma y, if the function is such that it takes x comma y to ux comma y vx comma. And if the corresponding thing would be to say that z goes to u x plus iy, which is equal to z goes to ux comma y plus I v x comma y. But and as a real differentiable function, that means if we consider f to be a real differentiable function, then we see the existence of this would be equivalent to the existence of this limit, which is just rewriting the previous expression again, right? Uh, but C itself, so there's a difference here. So in the case of real differentiability, when we talk about R2 to R2, here in the denominator we have norm of H, which is H1 square plus H2 square, and square root of that. But C itself is a field, and it makes sense to talk about division in that field, right? So as complex differentiability, what should be interested in is this limit going to 0, or this limit existing, right? Not just in the denominator should not just have norm h, but it should have h itself. That means the denominator also should be allowed to go to 0 along different directions. So if we think of the C plane as this, and this is the imaginary axis, and this is the real axis, then we should be allowed to go to the origin along different directions, right? Uh, which is in some sense not captured by this definition completely, because here in the denominator we have norm. So this is all parts, the stuff that we already know, that when we in this expression, this expression, when we take h2 to be equal to 0, we get u a1 h1 comma a2 u a1 a2 plus I v a1 plus h1 comma a2 v a1 a2, and this actually ends up being ux a1 comma a2 plus I times vx a1 comma a2. And similarly, if you take h1 equal to 0 and then take the limit, we end up with uy a1 comma a2 plus I vy a1 comma a2 upon ix upon I, which is equal to minus I uy a1 comma a2 a1 comma. And then when you compare these two notions, these two equations also part complex, and then they are equal, we get the well-known Cauchy-Riemann equations, which is ux equal to vy and uy equal to minus v. And so this is a popular thing that we all cover in our one variable case. Now let's look at try to understand holomorphy in another way, or at least in the one variable case. So we said that when we talk about functions from Rn to Rm, we want to be able to, it's differentiable at a point if we can approximate f of a plus h minus f of a by a linear map. In particular, this dfa is an R linear map from Rn to Rm. But when we are interested in C to C, then instead of, when we want to approximate this by a linear map, then this linear map now, so say it is th, some linear transformation t, it should be a C linear map. That means a linear map from C to C. So let's see what are C linear maps, right? So this is going to be these maps are the from Z going to alpha Z, and so for alpha equal to, so if you just compare it to the real, so this is, if you consider the corresponding thing from R2 to R2, then this is x plus iy going to a plus ib into x plus iy, and this is ax minus by plus I times bx plus ay. And when you write this as a transformation, this is going to be a minus b. So this is x comma y going to a minus b, and ba, right? So this is how we say that this is what the linear map should be. But since the reason all complex differentiable functions are also going to be real differentiable in the usual sense,
Hello.
what we have is that
Sorry to
the
interrupt.
Jacobian in fact
Uh,
looks like, yeah, yeah, yeah.
Actually, your voice is bit breaking, and also the presentation became a bit hazy. Actually,
Okay, okay, sorry. Okay. Uh, okay. Uh, is it okay now, or okay, one second. Let me just change the Wi-Fi. Okay, I hope it will be smoother now. Let's see. So
yeah,
what
it's
we were
okay.
talking about was yeah. So what we were talking about was C linearity. And what I was saying was that such a holomorphic functions, I want to look at holomorphic functions or get to the Cauchy-Riemann equations in an alternate way. And in particular, we want to think about what happens when the linear transformation, which is approximating the complex function fa plus h minus f of a, is in fact a C linear transformation. And when this is the case, we saw that we want the linear transformation to be of this form. But since real differentiable functions are complex differentiable functions are also real differentiable, this linear transformation will still have the form of the Jacobian. So we'll have ux, uy, vx, vy. And so when we compare these two forms, we get that in fact ux should be equal to vy. So that means these two are a. So then these two will be equal, and uy should be and uy will be equal to minus vx, which gives back the Cauchy-Riemann equation as expected, right? So this gives us an interesting way to think about holomorphy for the functions from Cn to Cm, right? So how should we go about defining holomorphic function from Cn to Cm? Well, the idea should be that we should be able to approximate the function f using linear transformation, such that the linear transformation t at the point a, so let's say I have some dfa and this at the point a from cn to cm is in fact c linear. That's what we want to be able to say. And again, the DFA, since real differentiability, complex differentiability should imply real differentiability, the DFA will still be the Jacobian, but the Jacobian should be such that it satisfies C linearity, right? So we wanted to satisfy C linearity. So let's see what that ends up saying in terms of the individual entry. So if we consider a function from f from Cn to Cm, so again, I will say that we can treat Cn and Cm as R2n and R2m, and at least topologically, and then the complex number, so the complex vector z1 zn, I will write it as x1. So this is same as saying x1 plus I y1, xn plus I yn, and this over here will be equivalent to, when treated as vectors in R2n, this is x1 y1 xn yn, and this is going to go to say u1 plus I, so u1 v1 and umvm, right? So when we write the Jacobian of this expression as functions from r2n to r2m, what we get is well, u1 x1, u1 y1, and so on. Similarly, u1 v1 x1, and so on, etc. So when we say, suppose we want to give conditions on these entries ui and vi and their partial derivatives such that it is C linear, right? This transformation should be C linear. So how can we go about doing that? So or what is the consequence of that? So if we consider the vector z1 to zn to be equal to the canonical jth vector, that means ej that has one at the jth location, then when we look at it in R2n, then the form will have one in the 2j minus 1 location, right? So this is 2j minus 1, and when we say iv1, then this will be I in the jth location, and the corresponding thing in R2n will have one in the 2jth location, right? So now if we say Jacobian of f, the C linearity condition would be that Jacobian of f into I v1 will be I times Jacobian of f into v1. And let's see what that translates to. So when I multiply Jacobian of f with when I multiply Jacobian of f with this row vector, then the row vector will have the form, right? So the row vector will have the form. We'll pick the xjth entry from this matrix. So this is u1 xj. So we have u1 xj, v1 xj, uh, and so on till um xj and vm xj. Yeah. And I times of this thing, which will be this is Jacob. So this will be Jacobian of f into v1. So let me rewrite this. So this is Jacobian of f I times this, and this side we have Jacobian of f into I v1. I v1 is to jth location. So here the derivatives will be with respect to yj, right? So u1 yj, v1 yj, and um yj, and vm yj, right? So now, what does it mean to multiply I with this vector? So recall that if we have a1 a plus I a1 plus I b1 till am plus I bm, and we are multiplying it by I, so we get this is minus b1 plus I a1 minus bm plus I am, and then so the corresponding vector in R2n will actually be equal to minus v1 xj minus u1 xj minus Vm xj minus, sorry, this is not minus, minus Vm xj uh, Um xj. So what when we equate these two, what does it mean? That we have U1 xj is equal to, so you want to equate these two. So we have U1 U1 xj equal to V1 yj, and or in general UK xj equal to VK yj, and UK yj yj equal to minus vkxj, right? So this actually, what this is showing is that when we want to impose c linearity, what ends up happening is that in fact the function, so the functions fk, which is actually uk plus I times vk, is holomorphic with respect to xj, or with respect to zj, when all others are kept fixed. All others are kept fixed. So C linearity is actually corresponding to each of the functions being each of f1, fm being uh, being holomorphic with respect to each variable separately, right? And this is what ends up being the definition of holomorphy for functions from Cn to Cm. That means if you have function from Cn to Cm, or an open subset of Cn to Cm, then f is holomorphic. So this is of the form f1 to fm, and then fj is holomorphic if fj is holomorphic with respect to each zk separately, right? So keeping this definition of holomorphy in mind, first we will go and see some examples of uh, or some ways in which the one variable case matches the several variable case, and then we will move to two important cases where they are completely different. But before going ahead with that, let's see some important geometric objects, so which you will keep on using. So the first thing is the complex hyperplane, which, as expected, given a non-zero vector in Cn, and some b in Cn, then the complex hyperplane passing through B, or defined by B and W, is given by all uh, Z in Cn, such that summation Ci Z minus Zi minus Bi I equal to 1 to n is equal to 0. The usual way in which we define a plane, but this is now the complex. So Ci is a complex number, Zi minus Bi is also a complex number, so this is a complex one. The next is the n ball, which is Z such that mod Z minus A is less than R, where this mod is Z1 minus A1 square plus Zn minus An square is less than R. And the n polydisk, which is this is written as delta n AR, which is Z1 Zn, such that this is in Cn, such that Z1 minus A1 is less than R1, Zn minus An is less than Rn. So in some sense, the n ball is a generalization of the n polydisk. And finally, the n torus, which is the boundary, or part of the boundary of the n polydisk, which is when each of the, so this is Z1 to Zn, such that Z1 minus A1 is equal to R1, and Zn minus An is equal to Rn. And I leave it to you to think about why this is not the entire boundary, and only part of it. In fact, a very special part of it, as we will see. So with these objects in mind, First of all, recall that in the one variable case, very important formula which is used again and again is the Cauchy integral formula, which says that if you have some open subset of C and f is holomorphic on omega, this will be my notation for holomorphic functions on open set. So if f is holomorphic on omega, then we have, and for all balls which are contained in the open subset omega, uh, we have fz is equal to 1 by 2 pi I f xi xi minus z d xi, the integral over the boundary of the ball. So oftentimes we write this, and if it is simply connected, if the domain is just to, for people who know, if the domain is simply connected and the ball is homotopy, boundary of the ball is homotopy equivalent to, so this is for all z in BAR. Yeah, and so if the boundary of, if this is homotopy equivalent to this, that means or homotopy to, that means I can deform the boundary of the ball to the boundary of the entire domain. Then in fact this integral can be written as, instead of CAR I can write del omega. And so the important thing is, I mean, at least for me, the what is interesting is that I'm able to talk about the values of the function inside the domain just based on the values of the function on the boundary. And there is a more general version of this where we have the nth derivative, which is n factorial upon 2 pi I f xi upon xi minus z bar n plus 1 and d xi, right? And this is on the boundary. So interestingly, first of all, since we have holomorphy in each variable, I mean, by definition, what we showed, what we have defined, the way we have defined for a function f now, which is a which is defined on an open subset of Cn to Cm, and if f is holomorphic on omega, then we have what we have said is that means that it is holomorphic in each variable separately. And so one would expect that the Cauchy integral formula would hold true in this case as well, because you fix one of the all the other variables and write the Cauchy integral formula with respect to one of them, and then we can uh, now have a new function in that complex variable and repeat the process. But recall that there is some subtlety here. When we are talking about the multiple integrals, we often want continuity. So and a priori, it is not clear that or that each of the function would be holomorphy would imply continuity in each variable. So we've given additional assumption. So if f is an open sub or defined on an open subset from Cn to Cm, f is holomorphic on omega, and f is separately continuous in each variable, or sorry, f is continuous overall, so not separately. Of course, it's separately continuous because it's holomorphic in each variable separately, but f is also continuous as a multivariable function. So as a multivariable function, then for all polydisks which are contained in omega, the and for all z belonging to delta NAR, we have so this is, recall, this is z such that z1 minus a1 is less than r1, zn minus an is less than rn, right? So now for whenever this is true, for whenever this object lies inside omega, we have this multi-Cauchy Cauchy integral formula, which can give you the value inside. And note that the order of the integrals and being able to write it in this form is uh, when in the naive proof is dependent on the continuity as a multivariable function. But later on it was proved by Hartog that this continuity is superfluous, and just having separate holomorphicity is enough to give this result. But that proof, even though people have been, this was proved in 1905, and but even though people have been trying for many years, there is no simpler version of that proof, and that proof is quite complex. So well, yeah, as you expect things in complex analysis to be. Anyway, so and similarly, how we have an expression for the derivative, we also have an expression for the derivative here. So let's like look at this thing a little bit more. So derivatives of complex functions or multivariable functions in general would actually be mixed derivatives. That means partial derivatives with respect to each of the variables. So and so, for example, if recall, if you have a function from say R2 to R, and you want to talk about the third derivative, so it can be of the form, there are many third order derivatives. One of the derivatives, for example, would be del cube f by del x square del y, right? So that's why, and this 2 comma 1 represents my alpha over here, and mod alpha is the order summation of all of them, and this kind of expression holds true. So I am sort of rushing through these parts because it's not particularly interesting to know why, in what ways it's similar to one variable. It's more interesting to talk about how it is different to one variable, but it's just to get some relation with what we already know. I'm going to go through this. So yeah, so this kind of Cauchy integral formula holds true. Now, next thing is the holomorphicity and whether it implies analyticity. As we know, we have seen many examples that. So first of all, let's recall what is the meaning of analyticity. A function is said to be analytic at a point if, or well, in an open set, if around that point A, so we contain there is an open interval or an open set containing A such that we can write f as a power series expansion z minus a power n is equal to 0 to infinity f of z for all z belonging to u, right? And this is again something that we are all familiar with. And in the real variable case, we all know that holomorphicity, or well, differentiability in that sense does not imply analyticity. So for example, consider the function e power 1 by x for x greater than 0 and 0 for x equal to 0, and we have seen that uh, so this should be minus 1 by x, I think. Yeah, so yeah, so e power minus 1. So we have seen that f n, nth derivative of f at 0 is equal to 0 for all n, but there is no Taylor series expansion, which so if there was a Taylor series expansion, it would say that f of x is equal to 0 in an interval in an interval containing 0, but that is not the case because every interval containing 0 has non-zero values. So of course, in real variables, infinite differentiability, or even infinite differentiability does not imply analyticity. On the other hand, for one complex variables, we do know, and this I think a proof of this will follow from expanding the Cauchy integral formula, and writing the Laurent series for 1 by xi minus z for in the appropriate domain. We in fact get that holomorphicity does imply analyticity. That means that if f is holomorphic in omega and a belongs to omega, then for all disks which are contained in omega, we can write fz equal to summation an z minus a power n, where an is equal to uh, 1 by 2 pi I f xi upon xi minus z power n plus 1 d xi, and this is del var. Right? So this kind of power series expansion exists, and as one would expect, since the proof of this existence comes from the Cauchy integral formula, and the Cauchy integral formula does hold true for several complex variables, holomorphicity does imply analyticity in the several complex variable case as well. But what do power series here look like? So the scenario is the same, that for an open subset, if f is holomorphic on omega and a belongs to omega, and there is a polydisk uh, which is contained in omega, then we can write fz in this form, right? So this is the way the power series would look like. So these are the indices, and these are the coefficients, and this is the power series, and the coefficients will be of this form, which come from the Taylor expansion as we saw. One thing that I missed pointing out is that see, here when we were talking about the Cauchy integral formula, we were talking about the boundary of the domain, or the boundary of the ball in which is containing A. But here we are talking about the integral being over this object, which is CA1 R1 cross CA2 R2 CA and Rn, which is a torus, which is not, as we discussed before, or as I have left as an exercise, that it is not the entire boundary, it is a part of the boundary of delta n AR. Because, for example, the boundary will involve objects of the form, say Z1 Zn, where Z1 minus A1 is equal to R1, but Zj minus Aj is less than Rj for j equal to 2 to n. So this is the point of the boundary, but uh, it is not in the torus, and so this is even stronger. We just have to integrate over part of the boundary to get the value inside the the sphere. I mean the polydisk. Right. So analyticity holds. So now we come to the identity principle, which is a very powerful application of the power series, or the fact that holomorphicity implies analyticity in the one variable case. So recall that we have that if we have an open subset of Cn and F is holomorphic on omega and A is a subset of omega which has a limit point, then and F of Z F, let's say, and F and G are in this, then F of Z is equal to G of Z for all Z belonging to A. Then of course we know that F is identically equal to G on omega. That means the value matches at all points on the open set. Well, it is immediately clear that this is not going to hold true in the multivariable case as it is. For example, consider the function F of Z1 Z2, which is equal to Z1. uh, this function is clearly holomorphic. It's separately holomorphic in each variable, and so this belongs to O of Cn, say. But and f of so if I take A to be equal to 0 cross C, then f of Z1 Z2 is equal to 0 for all Z1 Z2 belonging to A. But clearly f is not identically 0, right? So there is something slightly different going on here. Having limit point in A is not sufficient, but there is a slightly stronger version, which is that, or well, however you like to think of it, weaker, stronger, that if omega is a subset of, so this should be just C, this was only for C. If omega is a subset of Cn and U is an open subset in omega, and f of Z is equal to G of Z, for all Z belonging to the open subset, then F is identically equal to G. Of course, this should be connected. So then F is identically equal to G on omega. Right? So in some sense, you can always find subsets of uh, which have of Cn, because there are more dimensions. You can find subsets which have which have limit points, but are not as not of the same dimension as the entire set, right? As entire Cn. So in particular, so for example, A is sort of a one dimensional object in C2, right? But we have more moving room, so we have to put sharper constraints, and so we need something which is of the same dimension. And of course open subsets are sort of submanifolds, and they're the same dimension as the dimension of Cn, so it makes sense that this would be the case. So and just as a passing remark, I will mention that maximum modulus theorem, and to for those people who are more familiar with the one variable case, maximum modulus theorem and open mapping theorem do hold true for the several variable as it is. That means the boundary, the maximum, if the maximum is attained on the interior, then it must be a constant function. And for holomorphic functions, image of holomorphic functions for holomorphic functions, image of open set is open. So without going much deeper into that, let's go into areas which are more different. In particular, the first of these is analytic continuation. So what is analytic continuation? So let's start with what we know, or in for any open subset in Cn. So suppose you have any open subset on Cn and F is holomorphic on omega, and consider A in omega. Now we can talk about the power series of F. So let's assume that there is a polydisk inside omega. Then we can talk about the power, since it is holomorphic. F is holomorphic. We can talk about its power series. but it is possible. So let's consider this set. So U is equal to union of all polydiscs on which the power series of F converges. Right? The power series of F converges, and it is possible that these polydiscs are a subset of Cn. So it is possible that this polydiscs or their union in fact goes outside the open set omega. In for example, just consider the one variable case. So if you consider omega to be the ball b01 and f to be equal to say fz is equal to z, then of course this is actually convergent or has a power series in this is its own power series. That means z is the power series expansion everywhere, right? It holds true everywhere, and so u is actually Cn. Right? So it is possible that the power series converges outside omega, and in particular this is what we are interested in, that if we have f is in holomorphic on omega and u is some open subset. So okay, let's say v is some open subset such that v intersects the boundary of omega. So v intersection del omega is non-empty. uh, then does there then then does there exist does then okay, so well then if there exists G which is defined on V intersection V union omega such that G is holomorphic on V union omega, and G restricted to omega is equal to F, then G is said to be the analytic continuation of F. Right? So that means the power series corresponding to F is converging even at points outside omega, in particular at points in V. Right? This is like I said, this is the first part where we will see a very big difference. So in the case of C, so for n equal to 1, let omega be any domain. So domain, recall, is open subset. So open subset, any domain. Then we can always, and let B be a boundary point, right? And in particular, this is a point which is not in omega because omega is open, and we are interested. Boundary points will not be in the open subset. So this is we want to show that we can always find a function which cannot be analytically continued. So consider the function 1 by f of z upon uh, 1 by z minus b, and this cannot be analytically continued to any open subset u which intersects the boundary, right? View not, yeah. But and in fact there's something stronger which one can show, that there exists f which is defined on omega, um, and which is holomorphic on omega, such that uh, it cannot be. So here for each point b we have found a function, say fb, right? But there is something more which is true, that is there is a function which is holomorphic on omega such that it cannot be extended beyond any point. So the same function can work for all the points, right? So that means that if there's any open subset which intersects the boundary of omega, then that same function cannot be extended, right, for n equal to 1. But in the case of so this is here the domain was general, so that means for every domain such a function is always possible. But this is no longer true when we go to n greater than equal to 2. I am going to now state some theorems
Uh,
which will,
Excuse me, sorry to interrupt, but
yeah,
what you have written, I am a little confused. So
yeah,
you say given any b on the boundary,
right.
you have a function which cannot be extended to any open set. So
which
do you mean?
intersects which intersects at that point, like b belongs to
Yeah,
u
okay, right,
intersection del. Yeah, so
right,
that
right.
is what the initial construction is. But in fact we can construct a function which will work for any open set u intersecting the same function.
Right.
Like the first example is for each point you have to construct a separate function, but yeah, if we go deeper into theory then we can in fact find a function which works for all open sets.
All right, thanks.
Yeah. For n greater than equal to 2, the first theorem is the Hartog spherical shell theorem. right? So what does this Hartog spherical shell theorem say? That for omega equal to bar minus ba rho closure, where 0 is less than rho is less than r, every function f which is holomorphic on omega can be extended analytically to the entire ball, right? Which is a very special thing. So, for example, if we had gone to the one dimension, so this clearly doesn't hold for n equal to one. So, for example, what would be a corresponding thing in n equal to one would be an annulus. So the corresponding function would be an annulus. So if we have, I mean, the corresponding domain. So if we had b01 minus b0 half closure, then the function f of z equal to 1 by z clearly is holomorphic on omega, but does not have an analytic continuation to entire B01, right? But surprisingly, because there is more moving room in a higher dimension, in fact, this is true. And when I was discussing this sometime earlier with someone, they had said, so what if you consider, so if n is equal to 2 and you consider the same set, say B0 half closure, and we consider the function f of say z1 comma z2 equal to 1 by z1 square plus z2 square, then how can you say that I mean of course this function is not defined at 0, and so it is not defined entire, I mean it's not holomorphic or entire b01, so one would, so by the above theorem we should be able to say that it's not in fact holomorphic in omega also, so this is omega. So but can we clear, can we immediately see, so one has to be careful that these are complex numbers. So for example, if I consider z1 z2 to be equal to say 3 by 4 root 2 comma 3 I 3 by 4 root 2, so what is this value? This is so if I take the modulus of this, so this is going to be 9 by 32 into 2, so this is going to be 9 by 16, which is 3 by 4. So clearly this is in this set, but f of z1 z2 is in fact equal to 1 by 0, or rather not defined because of the I which is present here. So what I'm the point of this example is that the more since there is more area, more dimensions to move around in, um, the being holomorphic is sort of a sharper condition, and so we are able to get more stronger results in this case, right? And at least that's the intuitive way to think about it. Another interesting result, which will lead to something even more interesting, is the following, that for n greater than equal to 2, if f is holomorphic, so let's say f is holomorphic on D, where D is equal to the polydisk minus the point A, then F is holomorphic. F is holomorphic on D itself. Sorry, on the entire polydisk. Again, this is in sharp contrast to what we would expect in the one-dimensional case, because you remove a point from B01 minus 0, then of course 1 by z is holomorphic on this, but not extendable on the entire thing. But this gives a very interesting consequence, that note that the function, so if f is from omega subset of Cn to C, then f cannot have isolated singularities. So why is that the case? Because if it had isolated singularity, so suppose z naught is an isolated singularity, uh, singularity of omega, then what we will find is that delta n of, so there will be some polydisk, some open set, some polydisk around z naught, say some radius r minus z naught, on which on which f is holomorphic. But then by the previous result, that would force f to be holomorphic on the entire set. But that is of course not possible, because z naught is a point of singularity. So that means this cannot have any isolated singularities, and as a consequence, any function f can from open subset of Cn to C cannot have isolated zeros as well, because if it had isolated zeros, then 1 by f would have isolated singularity, and they would be done. But this is exactly opposite of what happens in the one variable case, where a holomorphic function must have isolated zero if they are non-zero, right? Otherwise they are the zero function. So in this sense we are in complete uh, opposite behavior as compared to one variable case. And another thing I would like to point out here is that I am not going into details of the proofs, but at the end I will cite some references, and you will find in the proofs that uh, uh, all the proof techniques you essentially use single variable analysis, but the results that we end up getting are in complete contrast to the several complex case, or to the single variable case, right? Um, yeah, and the last result that I want to state is that in this analytic continuation is that if D is defined as is so if D is any open subset, so or domain, so open subset and connected, so open connected subset of Cn, and K is a compact subset of D, then and F is holomorphic on D minus K, then in fact f has an analytic continuation as an analytic continuation to D. This is like a generalization of the previous two statements, and it's called the Hartog Osgood uh, uh, Hartog Osgood Brown theorem, right? And yeah, so these three theorems give some very interesting aspects of analytic continuation in several variable case. So now let's move to a related topic, which is the domain of holomorphy. So we talked about the function, which we showed that for every point we are able to find a function which cannot be extended beyond that, and that in fact is the definition of a domain of holomorphy. So for omega in subset of Cn, it is called a domain of holomorphy. So maybe from now on I will write DOH if for every connected domain or connected open set U such that U intersection boundary of omega is not empty, and for every connected component omega 1 of omega 1 of U intersection omega, there exists f which is holomorphic on omega such that f cannot be extended analytically to U union omega. So I mean, ignoring uh, this every connected what it's basically trying to say is that if you have some domain like this, and you have U which intersects it in sort of two parts, then this connected component and this connected component are sort of treated separately, and for each one of them it's okay to find different functions. But I mean, that's some corner case. Essentially what we are trying to say is that for every point we should be able to find some function which cannot be extended analytically beyond that point, right? And by the same example as we discussed in above, the 1 by z minus b, we can say that every domain in C is a domain of holomorphy. But of course, that is not true in the case of Cn, because as we saw, for any domain D, if you consider D is in Cn n greater than equal to 2, and K is a compact subset of D, then the boundary of D will also contain. So as a representation, this is not a 2D object, this is at least a 4D object. So if you consider this as D and this is some compact set K, then this part of the object is also going to be part of the boundary. And then in fact, every function, by what we saw, that if every function is every function which is holomorphic on omega does extend to D, right, to entire D, which means that there are parts of the boundary for which there are no functions which cannot be extended, right? That means for these parts of the boundary, every function can be extended. So such a domain is not a domain of holomorphic, right? Now, before going ahead into so that we have some background for convex geometry, because there is very many deep connections between convex geometry and domains of holomorphy. So I will just recall some facts about convex geometry. So recall that a subset C in Rn is said to be convex. Is said to be convex if for a comma b in Rn, 1 minus lambda a plus lambda b for all lambda in 0 1 is also in Rn, is also in C, right? So if for all a comma b in C, 1 minus lambda a plus lambda b is also in C for all lambda in 0 comma 1. So this is we already know this definition. The first theorem that I would like to, or the result that I would like to recall from convex geometry is the supporting hyperplane theorem, which which geometrically, which I think rather than stating it very rigorously, I'll just give a geometric idea for what's happening. That means, so if we have a compact subset, if you have a convex set C, so this is my convex set C, and this is which is C in any Rn, then and there is a point say x naught, which is a boundary point, then what the theorem says is that there exists a non-zero vector in Rn such that for all x belonging to C, x minus x naught comma w is less than 0. So that means that for every point which is in the interior of this convex set, this angle is obtuse and going to give have a negative cos sign, and that's what this supporting hyperplane theorem says. It particularly guarantees the existence of this plane which is defined by omega and x naught. And the next as so this immediately gives us a hint on an interesting thing, that all convex sets, so all convex subsets of Cn are domain of holomorph. So why would that be the case? So well, consider the point. So first of all, let's see how to write this dot product. So this was a real dot product, and what we are interested in is the real dot product being negative, because any subset C which is in Cn can be considered as a subset of R2n, but the dot product that we will be interested in is this real dot product. So let's first of all see that what happens if we take so if we have a vector x1 y1 xn yn, and we take the dot product with a vector alpha 1 say beta 1, so alpha 1 minus beta 1, alpha n minus beta n, or okay, alpha n beta n, then this is the usual real dot product will be summation xj, so let's say x1 alpha 1 till xn alpha n plus y1 beta 1 till yn beta n. So this will be the expression, but in the in complex case, these are complex variables x1 plus iy1 xn plus iyn, and you take dot product with alpha 1 plus I beta 1 alpha n plus I beta n, then this is a complex dot product which is going to be x1 plus iy1 dot alpha 1 plus I beta 1 and xn plus iyn into alpha n plus I beta n, and we are interested so instead of, so this will, the real part of this will give me x1 y1 minus alpha 1 beta 1. So let's say, suppose I'm interested in the real part of this, so this will be the real part of this, and this will be x1 y1 minus alpha 1 beta 1. So to counter that, what we will take is the minus vector here. So this is the x1 plus x1 y1 plus alpha 1 beta 1 um, plus x2 y2, sorry, x1 alpha 1 plus y1 beta 1, x2 alpha 2 plus y2 beta 2, and so on. So what it means is that if I want to take the dot product of two vectors, I take the complex conjugate of the second vector and then take the real part of the complex dot product. Keeping this in mind, So now consider a convex subset in Cn, and let x naught or z naught belong to the boundary of, let's say this is convex open subset, so let this be the boundary. And now consider the function given by f of z equal to 1 by, so at z naught, as we say, since omega is convex, so this is convex. So at z naught, there is a supporting hyperplane, and so the normal vector of the supporting hyperplane, let it be given by alpha 1 beta 1 alpha n beta n, and so we call, let small c be the vector which is alpha 1 minus I beta 1 alpha n minus I beta n, and so we have c dot z minus z naught as the function that we are interested in looking at. So clearly it's a holomorphic function, and uh, and note that for all z in C, since C is in omega, since omega is convex, the real part of C z minus z naught is less than 0, which means that denominator is non-zero. So f is holomorphic on omega, but it cannot be extended analytically. So all convex subsets are in fact domains of holomorphy. So this is the first sign of some interaction between convex domains and domain of holomorphy. But just to be careful, all domains of holomorphy need not be convex. Only all convex subsets are domains of holomorphy. There can be domains of holomorphy which are not convex. Um, the next notion that I would like to define is the convex hull. So let for any set, so let K be a subset of Cn. Then the convex hull of K, if you recall, is the intersection of all convex sets containing K, which is basically the same as the smallest convex set containing K. And there is a result in convex geometry which tells us that for any compact subset of Cn, um, so convex hull of K is the intersection of all closed half spaces containing it, so containing K. But what does this mean? Again, getting some geometric intuition about it will be useful. So if suppose my uh, compact subset is something like this, say this is my compact subset, which is clearly not convex. I can take 2 points, 1 point here, 1 point here. Line segment is not in the set. So I want to find the convex hull of this. So uh, for each point on the boundary, I will or for each point in Cn or in R2n, I can find a normal. I can consider normal vector and a plane which passes through it, right? And this hyperplane will divide my thing into two parts. So one part will be this side, one part will be this side. So if for all x belonging to K, x minus, suppose this is the point x naught, this is the vector w, so x minus x naught comma w is less than equal to 0, then I say that if this is true for all x in K, then I say that um, this half space contains K. So the half space H contains K, right? So similarly you can, so what this is saying is you consider all such half spaces, and then basically you keep going closer. So there's a plane here, similarly there will be a plane here, but for example a point here, it all we cannot have, so so eventually, we will so for a point here, again you consider the half space, so everything will not be contained in one half space, but if you go here, then in fact everything is contained in one half space, and then you consider the intersections of it, so on, and then eventually you get the convex hull, which is what we expect it to be, right? So the intersection of all closed half spaces containing K in fact is the convex hull of K for every K which is compact, right? And this gives an interesting characterization of compact sets, which we will see. So first of all, note that instead of considering all compact sets, what we all closed half spaces, so let's see, so this was the This was the convex or the compact set that I was considering above K. So instead of considering all half spaces, what we can do is consider the half spaces which are the closest to it, right? So that means those which are sort of just about passing through the points on the thing, right? And what we know is that x, so the way this closed half space is being defined, that everything is contained on one side. So what we want is that for all k in um, for all x in k, x minus x naught comma w, for which is the defined in the half space, is less than 0, right? Which means that x comma w is less than x naught comma w. And when this is true for all k, so in particular k will be in the convex hull of k, but in fact all points of the convex hull of k will also satisfy this aspect, right? For example, if I have this this plane, so if I take this point x naught and this plane satisfying it, then all points of k don't satisfy. But if I have taken this point and this half plane, then all points of k will satisfy, and on in fact all points of the convex hull of k will also satisfy. So an equivalent characterization is this, that is, the convex hull of K is all x belonging to, say, let's switch to Cn, so z belonging to Cn, such that z comma w is less than the supremum of, so this is the maximum value that we can take over entire K, right? So supremum of z comma w for all, so xi comma w for all xi belonging to K, um, where and for all, so this is for a fixed normal vector w, but we can vary over all to get all the hyperplanes, we can vary over all hyperplanes. So this is all w belonging to Cn. So this is also the convex hull of K in Cn. um, but so how can we rewrite this? So this is a real dot product, so this is the real dot product, this is the real dot product. So recall we had seen that this is the same as real part of z comma omega bar um, is less than supremum of xi comma k, real part of xi dot omega bar, where this is now the complex dot product for all omega in Cn. And now this is, so since we are taking all omega in Cn, this omega bar can be removed, and so this can be rewritten as exponential of, so mod of, so remember e power x plus iy mod is equal to e power x e power iy, which is e power x, which is e power real part of z, right? So e power z mod. So since using this, we can write this as mod of e power z dot w is less than e power xi dot w supremum over k, k supremum, omega belonging to Cn. So this is another way to write the convex hull of K using a holomorphic function. So this is a holomorphic function, right? But one could generalize this notion, and the generalized notion would be that convex hull of, we define the following, which is the holomorphic convex hull of K as a subset of omega is all the, so this is represented as k omega hat, which is all z belonging to omega, such that uh, fz is less than norm of f xi, or supremum of f xi over all xi belonging to k, um, for all f belonging to, which are holomorphic on omega. See, this is a sharper set than this. Here we are only considering specific holomorphic functions. Here we are considering all holomorphic functions, right? And this domain of, this is known as the holomorphic convex hull of omega. And just to, since we are running out of time, just to give one final result, state one final result which will drive home the this is the holomorphic convex hull, and a domain D in Cn is said to be holomorphically convex. So holomorphically convex if for all compact subsets K of omega, the holomorphic convex hull is also compact. Right. Now I will give two. Now for any compact subset, for any say any omega in Cn or Rn, the following are equivalent. So this is an equivalent characterization of convex sets. The following are equivalent. The first is that omega is convex, normal convex, not holomorphic convex, just the normal sense of convex. Omega is convex for all compact subsets of omega. The convex hull of K is also compact. Convex hull is also compact, and for all compact subsets of omega, the distance between the compact subset K and the boundary of omega is equal to the distance between the convex hull of K and the boundary of omega. And now the theorem which gives the relation between, I mean the similarity between convex geometry and this, which is the Cartan-Tholen theorem, which says that for open connected subsets of Cn, so omega is open connected, open and connected subset of Cn, the following are equivalent. First, omega is a domain of holomorphy. Two, omega so uh, omega is holomorphically convex. That is, so by definition of holomorphically convex, for all compact subsets of omega, the convex hull of omega is also compact. The convex hull of K in omega is also compact in omega. And finally, well, last two parts. So yeah, the convex hull, so omega, the distance of K from the boundary of omega is equal to the distance of the holomorphic convex hull from the boundary of omega. And the last part is that there exists a function f which is holomorphic on omega, and f cannot be extended analytically beyond any point. So that means, similar to the one dimension case, every domain of holomorphy, so domain of holomorphy meant for every point there is a function, but in fact that is equivalent to there being a function which cannot be extended analytically beyond any point, which is a stronger condition, right? And these two theorems, this theorem, which is a characterization of, which is a theorem from convex geometry, which characterizes convex sets, is very similar to this theorem, which characterizes domains of holomorphy. So all convex subsets are domains of holomorphy, and all holomorphically convex subsets are and all domains of holomorphy are holomorphically convex, right? So there is something deep going on here in the interaction between convex geometry and several complex variables. And this kind of interaction and this kind of results are not clearly not there in one variable case, because all domains are domains of holomorphy there. Um, yeah, so I think I will stop at this point since I already overshot. Uh, I hope that I could give you some interesting facts about several complex variables and sort of motivate you guys to study it a little bit. Maybe I'll list out some resources which you can access. So the main two introductory sort of notes which will motivate you further, which I also used to read, are: the first is by the famous analyst Stephen Krantz, which is the title of the article is what is several complex variables, right? And another article by an Indian author, whose name is Debraj Chakrabarti, who has written an article called "Several Complex Variables Are Better Than Just One." And finally, the main resource where you can find detailed proofs and all such things are is there is a set of there's essentially it's a book uh, which is several complex variables by Korevar and uh, Viger Vigering. Yeah, so just if you type Coreva several complex variables, it's a free PDF, free set of notes available. You can see this. And I would just end by saying one thing that some of you might think that the talk was too much analysis and not related to geometry or topology, but some of the there is a set of famous problems called the Coulomb problems in several complex variables, which whose solutions were initially presented from sheaf cohomology, which is a highly algebraic topological object of study. So yeah, just hope you guys find it interesting and want to take a look at it further. Thank you.
Thank you, Shonda, for this wonderful talk. Is there any question? Maybe we'll wait 1 or 2 more minutes if there is any question. After that, we'll end. Okay, if there are no more